Suppose you're sitting watching a movie in a comfortable business class seat on a flight from Atlanta to Rio de Janeiro. Are you sitting still? Or are you soaring through the air at 500 miles per hour? Or are you hurtling through space at 67,000 miles per hour? The answer to all of these questions is yes. You're stationary relative to the floor of the airplane, flying at 500 miles per hour relative to the ground below, and revolving about the sun at 67,000 miles per hour. Your velocity depends on the coordinate system it's measured in. In this mini lesson, we will work through in detail an example showing how the velocity of an object measured relative to one coordinate system is related to its velocity measured relative to another coordinate system that itself is moving relative to the first. First, however, a little review. A frame of reference is a coordinate system in which one makes position and time measurements of physical events. Two different frames of reference may be in motion relative to each other. Suppose we have two frames of reference, x, y, and x prime, y prime, that are in motion relative to each other. In particular, the origin of the x prime, y prime frame is traveling at velocity big V as measured in the xy frame. At some instant, say t equals 0, the x prime, y prime origin is located at position big R as measured in the xy frame. Then, if some object is at position little r prime as measured in the x prime, y prime frame, the position in the xy frame is little r, which equals big R plus little r prime, as the figure shows. As always, the velocity of the object is the time derivative of its position, regardless of which frame of reference the position is measured in. So the velocity vectors in the xy and x prime, y prime frame are little v equals d by dt of little r, and little v prime, which equals d by dt of little r prime, respectively. Furthermore, the velocity of the x prime, y prime origin relative to the xy origin is big V, which equals d by dt of big R. How are the velocities in the two reference frames, v and v prime, related to each other? Well, since the positions are related by little r equals big R plus little r prime, the velocities are related by little v, which equals d by dt of little r, which in turn equals d by dt of the quantity big R plus little r prime, which equals d by dt of big R plus d by dt of little r prime, which equals big V plus little v prime. Or putting it all together, little v equals big V plus little v prime. Okay, let's do an example. Samantha has to fly her private jet from Atlanta, Georgia to Lansing, Michigan, 1,000 kilometers due north, to attend a very important business meeting. It's an exceptionally windy day over the whole route, with a wind velocity of 60 kilometers per hour due southeast. Samantha's jet flies at an average airspeed of 480 kilometers per hour. Part A asks, in what direction should Samantha fly her jet? And Part B, how long will the trip take her? As usual, it's always a good idea to draw a picture of the scenario described in the problem. Here is a portion of a United States map with a straight line path 1,000 kilometers due north from Atlanta to Lansing. We're told that the wind velocity is 60 kilometers per hour directed southeast. We indicate this with a vector pointing 45 degrees south of east. We're also told that the jet has an average airspeed of 480 kilometers per hour. What does airspeed mean? Well, it means the speed relative to the air as opposed to relative to the ground. We indicate the jet's airspeed velocity by a vector 8 times as long as the wind speed vector, because 480 kilometers per hour is 8 times 60 kilometers per hour. But we're told nothing about the direction the jet should fly. In fact, that's one of the things we're supposed to calculate. Finally, there's the velocity of the jet relative to the ground. We're not told how fast that should be. That's another thing we'll need to calculate. But we do know that it should point due north from Atlanta to Lansing. Okay, let's relate this problem to the general expression for relative velocities that we derived earlier. It said that the velocity of an object in the xy reference frame, little v, equals the vector sum of two velocities. The velocity of the x prime y prime frame relative to the xy frame, big V, and the velocity of the object in the x prime y prime frame, little v prime. But in this problem, what are the two frames? In particular, what plays the role of xy and what plays the role of x prime y prime? Well, the xy coordinates are fixed to the ground, and the x prime y prime coordinates move with the wind or air relative to the ground. Little v is the velocity of the object relative to the xy frame. So in this problem, where the object is the jet, little v becomes the velocity of the jet relative to the ground. Big V is the velocity of the primed reference frame relative to the unprimed reference frame. So in this problem, big V becomes the velocity of the air relative to the ground. And finally, little v prime is the velocity of the object relative to the x prime y prime frame. So in this problem, little v prime becomes the velocity of the jet relative to the air. In summary, the relative velocity equation applied to this problem tells us that the velocity of the jet relative to the ground equals the velocity of the air relative to the ground plus the velocity of the jet relative to the air. With this in mind, let's draw a vector sum picture for this problem. We know that the vector v sub jet ground should point due north, but we don't know its magnitude yet. So we start just by drawing a north-south dashed line. Then we draw in the vector v sub air ground so that its tip is on the north-south line. We'll see why we do this in a minute. But since we know both the magnitude and direction of this vector, this part of the drawing is well defined. Now we have to deal with the vector v sub jet air. We know its magnitude but not its direction. But since v sub jet air plus v sub air ground gives v sub jet ground, which we know has to point north, we rotate v sub jet air, keeping its length fixed, so that its tail is on the north-south line and its tip is at the tail of v sub air ground. Like so. Now the two vectors are arranged tip to tail so that their sum points due north. Like so. We don't know the angle that v sub jet air makes with north, and we don't know the magnitude of v sub jet ground. But now we can use geometry to determine them. Let's simplify the picture by replacing it with a triangle, and let's label everything we know about the triangle. We know that the 60 km/h side makes an angle of 45 degrees with east, as shown. But what we really want is the angle between that side and the northward pointing side of unknown length. A little triangle geometry tells us that that angle is 135 degrees. I'll let you work through the little geometry exercise on your own, but if you get stuck, please be sure to ask. Now we have enough information in the figure to compute the unknown angle theta. We use the law of sines. In particular, the sine of theta divided by the length of its opposite side, 60, is equal to the sine of 135 degrees divided by the length of its opposite side, 480. Solving for theta gives theta equals 5.1 degrees. Now that we know theta, we can use it to find the third angle of the triangle. The sum of the angles in a triangle is 180 degrees, so the third angle is 180 degrees minus 134 degrees minus 5.1 degrees, or 39.9 degrees. We can now use the law of sines again to determine the magnitude of V sub jet ground. In particular, V sub jet ground divided by the sine of 39.9 degrees equals 480 divided by 135 degrees. Solving for V sub jet ground gives V sub jet ground equals 435.7 kilometers per hour. Now we're ready to answer the questions in the problem. In what direction should Samantha fly her jet? Well, that's just theta, 5.1 degrees west of north. And how long will the trip take her? Well, we know she travels 1,000 kilometers at a speed of 435.7 kilometers per hour. So the trip's duration is 1,000 kilometers divided by 435.7 kilometers per hour, or 2.30 hours.